Now I want us to look at RSA digital signature. We had looked at this one earlier, so it's just again revision. Some the new students who had requested we relook at it. Now I'll go to the algorithm just straight away, and of course, first of all, mention that the algorithm for the RSA digital signature is similar to the one of RSA algorithm that we looked at the other time. Now, so I want to begin by assuming that you want to sign some document. And so you see, the digital signatures are meant to ensure that after the document has been signed, it can be verified that that document was indeed signed by the person who claims to have signed it. Because there are cases where somebody could sign without the digital signature, somebody could sign for another one, or an intruder can sign for another person. But we want to have a case where it is verified that, in fact, the person who signed, who claims to have signed, is indeed the one who signed that document. And so we shall be looking at the same thing, the same algorithm as the one we did for the RSA. The only difference will come in at the time of signing, what keys we'll be using, the kind of keys that we'll be using at signing and so on. But just as we talked about the RSA algorithm, we said that we choose two numbers, prime numbers, P and Q. And of course, these two should be large enough, large prime numbers. Then after choosing these two prime numbers, you get their product N. After getting the product, you also get the Euler phi of N, which of course is P minus 1 multiplied by Q minus 1. Just the same way we did for the RSS algorithm, the same thing we are doing. Then after this, you choose E, the exponent E, and this number we said should be relatively prime to Euler phi of N. In other words, the GCD of E and Euler phi of N should be 1. So the E, you just choose it. You choose a number which is relatively prime to Euler phi of N. That will be the exponent. And of course, we said that after choosing this, after selecting P and Q are kept secret. We said they should be kept secret, those P and Q. And we say that after calculating this, N will be made public. Another thing that will be made public, another key will be E. It will be made public also. Now, the Euler phi of N should be private. Nobody should know it, because once somebody knows Euler phi of N, that person, as we saw last time, once you know this, you are able to get this P and Q. You're able to get P and Q, and once you get P and Q, then you're able to get the decrypting key, which is supposed to be secret. Now, so let's proceed. We've said you've chosen P and Q, which are prime numbers, and of course, for purposes of security, we say they should be large prime numbers. You've calculated their product, which is N. You've found the Euler phi of N. You've chosen an integer relatively prime to Euler phi of N. The next thing that follows, therefore, is to find the inverse of E mod Euler phi of N. The inverse of E. You are doing this using the extended Euclid's algorithm that we learned. So this is our D. This is supposed to be secret. It's in cases of the RSA algorithm that this is the decrypting key, but we shall give it a different name for purposes of signature. We shall give it a different name, but for RSA algorithm, this is supposed to be the decrypting key. Now, so what is made public? What is made public, we've said, is the N, the product of the two prime numbers, and the E. These two are made public, even for purposes of the signature. These two are made public. The private key is N and D, just as it was for RSA algorithm. Now, let's suppose that your message that you want to sign is N. The message that you want to sign is N. You have the keys. You have the public key here, and you have the private key here. And you have the message that you want to sign. So what you then do, you take your message, in this case, it's N. So if it's N, then let this be M. Let this be M so that we don't mix. Hello? You can hear me, is that okay?
Yes, we can hear you, sir.
It's okay, thank you. So what we said, the message you want to sign is N. So I'm just changing so that the product of the two numbers, our modulus, should be M. I just change so that our modulus becomes M, and so on, so that the private key is MD. Now your message that you want to sign is N. So therefore the signature is N raised to D mod M. N raised to D mod M. D here, remember, it was the inverse of E. Now, so that is the signature. So what is the signed document? The signed document, therefore, is the message that we wanted to sign, N, is this pair. This pair is what we call, let me call this one S, the signature. Let him call it S. S is the signature. So the signature is N raised to D. So, and therefore, what is our signed document? Our signed document is the document we had with S. That is the document you now send. So that's what I've just, that's those steps. Let me just go through the steps, the type steps, so that for the sake of noting, writing, but basically that is what we are going to do. Those are the steps. So the first step I said, since you want to send this message, N, the first thing you will do, you choose two prime numbers. And for purposes of security, we said they should be large prime numbers, and of course not equal. Then get their product. This product, we've said, will be made public, but P and Q will be private. The Euler phi of M. Since we are only talking of two prime numbers, since we are only two prime numbers, then the Euler phi of M will be P minus 1 times Q minus 1. And then after that, you just choose one number which is relatively prime, the Euler phi of M, of course, less than it, a number between 1 and Euler phi of M. and is co-prime or relatively prime to Euler phi of m. This number will be public. For purposes of digital signature, this E is used to verify that indeed the document we have was signed by the person claiming to have signed it. So it will be used to verify. Now, once you select this E, you calculate its inverse. And its inverse, we are calling it D. And of course, it should be between this range. So you do by extended Euclid's algorithm because, as you can see here, E multiplied by D is equivalent to 1 or is congruent to 1 mod phi of m, which means that D is the inverse of E. So we, of course, we shall look at examples. Now, so once you get the D and you have E, what do you make public? We've said you make public M, the product of the two prime numbers, and E. Those ones you make them public. For purposes of digital signature, they'll be used for verifying. This E will be used for verifying. And even this will be the mod at that time. Now, so your message was D, was N. You want to sign it, so the signature becomes N, the message. Of course, if it's in word form, you convert to integers, you convert to numbers. You convert to numbers if it's in word form. Now, so take this N, your message, raise it to D, the inverse of E, mod M. This is the signature. So the signed document, therefore, is the document that you had and the signature. This is the signed document. Now, so once you've signed, you send it to whoever you wanted to send, and that person will want to verify that this document, of course, has been signed by you. So how does this person verify? To verify, you take this signature and raise it to the public key, which is E. Raise it to E and see what you get. The answer that you get, let me call it maybe M1. The answer that you get, compare it to what you have here. Compare it to this. Compare and see if they're the same. What have you done? You've just taken this signature S. This signature S, you've raised it to E. E, you're finding it from public domain where the person had deposited the signature. You just found the E there. Take this E raised to the signature and see what you get. Of course, you're doing this mod M. You're doing that mod M. See what you get. Compare what you get with what you've been sent as the message. And if they are the same, it means it has indeed been signed by the person claiming to have signed it. So how do they become the same? I've just said it's S raised to E. S raised to E. But what is S? S is N of D. S is N raised to D. Now raise it to E. So what you get is N raised to ED or DE. But recall that E and D are inverses of each other, which means this is n raised to 1, which is just n mod m. So this is of course, this is how I show that they are the same, but in terms of calculation, that's what you'll not be doing. What you'll just be doing, you'll be taking the signature, as I've said, raise it to E, reduce it mod M, and then see whether that is the same thing you are sent, whether that is n that you are sent. I just want to look at a few examples just to make the point clear. Now, my first example is here. For each of the following, show how Ken would sign a message M using RSA digital signature algorithm with a mod N to obtain a signed document that where S is the signature and M is the document, M, the message. And we have been told that this Ken chooses a public exponent E. So in part A, Ken has chosen P to be 5 and Q to be that. And then he has chosen E to be 7, but the message he has to send is 6. So how do we find the signed document? First of all, you find N, the product of these two prime numbers, PQ, which will be 65. Then find phi of N. You will have phi of N, which is 5 minus 1 multiplied by 13 minus 1. And of course, this is 4 and this is 12, giving us 48. Now, we've been told that he has chosen 7 as E. So E is 7. So what we now do, we find its inverse. Find the inverse of 7 mod 48. And this you can do using the extended Euclid's algorithm. First of all, using the Euclid's algorithm. So when you do this, what you'll be getting is D. And remember what D will be doing. In terms of signature, D will be used for signing, and E will be used for verifying. So, and remember how we'll be signing. To sign, take your message M, raise it to D. Take your message M, take your message M, raise to D. And to verify, you're taking S and you're raising it to E. And all this, you are doing it mod N. Mod N. So those are the steps you want to go through. Those are the steps. So when I did the product, I got 65. When I did the Euler phi of N, I got a 48. And then find D such that 7 times D is congruent to 1 mod 48. And this we do using the Euclid's algorithm. And how do we do using Euclid's? We've done this before. We're asking ourselves, how many times does 7 go into 48? And 7 goes into 48 6 times. And the remainder is 6. And then we ask ourselves, how many times does 6 go into 7? This 6. And so it goes there once, and the remainder is 1. So once you reach here, the remainder is 1. That becomes the GCD. And since it's the GCD, to do Euclid's algorithm, we make that GCD the subject of that equation. We solve for the GCD. Just a minute. So when you solve for the GCD, you use from the last equation, you make 1 the subject. From this equation here, the equation that has the GCD, from this equation, make this 1 the subject. What do you get? 1 is 7 minus 6 multiplied by 1. And that's what I wrote here. So we've made the first remainder the subject. And what is the other remainder here? What is it? This other remainder, 6, is 48 minus 7 multiplied by 6. When you take this on the other side of the equal sign. So 6 is equals to 48 minus 7 multiplied by 6. Now let's come to where I'm doing my working. This is my working. So the first remainder, the first remainder here was 7 minus 6 multiplied by 1. So 1 is 7 minus 6 multiplied by 1. Then replace this other remainder. Replace the remainder by the equivalent, which is here. So when you come to the next step, you have 7 minus this minus, but this 6, instead of this 6, we write the equivalent, which is 48 minus 7 multiplied by 6. Then there's this 1. This 1 is just this 1 here. Now, at that point, now you open the brackets. You just simplify what you have here by opening the brackets. So how do you open these brackets? First of all, we know that we have a 7 here, and then there's a minus sign and a 1 outside. Minus sign and a 1 outside. So when I take them inside the brackets, what I get is 48, 1, that is minus. Then this minus times that will be positive, 7, and this 1 times that is 6, just be 6. And so that is the step you are seeing here. That is this step. Then from there, we collect like terms. The one, you can see 7s there twice. So this first 7, and there's the second 7. So this is what we have. In fact, when we bring the 7s together, this is what we have. So you can just factorize this part by putting 7 outside the bracket. 7 goes into itself once, and 7 goes here 6 times. So that means we have 7 times 7. That's what I have here. 7 times 7. Then I have this negative 48 multiplied by 1, which is just the same as positive 48 multiplied by negative 1. That's what I have here. So this is the final equation. Now, so we were finding the D. We are finding D. And by definition, D is that element or that number which, when multiplied by 7, gives us 1. That is the definition of inverse. The inverse of A, by definition, will be B if their product is 1. The inverse of A will be B if their product is 1. So this is what we have. This is what we have here. We have that, and it equals to 1. What we have is that 1 is equals to 7 times 7 minus 48 multiplied by negative 1. No, by plus. plus 48. So in other words, the number that is multiplied by 7 to give us 1 is 7. The number that is multiplied by 7 to give us 1 is 7. So 7 is the inverse of 7. So we wanted the inverse of 7. So that inverse is also 7. So that is our D. That is our D. So once we have D, or of course we already have E. So once you get E and you have M, the next thing, first of all, make them public. Then calculate the D. D will be used. So we now want to use the D to just sign the message. Let's find out what the message is. Our message is M6. Our message is here. 6. 6 is our message. So signing, we said we take the message and raise to D. Take the message and raise to D mod 65. This is a small number. Just take 6 raised to 7 and reduce mod 65. Let me just remind, if somebody has forgotten, let me just do that. That's a small number. Let me use my calculator. So using a calculator, these are small numbers, but I said for purposes of the signature and so on, and RSA, we are using bigger numbers. So what is 6 raised to 7? This is what I'm getting. 6 raised to 7, I'm getting 279, 936, and I'm doing this mod 65. In other words, I'm dividing by 65 and then writing the remainder. So let me just divide by 65. When I divide by 65, I find that it goes there for 4,306. I hope you are also using your calculator. So it goes there 4,306. But what I want is the remainder. So what is the remainder? So let me just do that. 4306. The remainder is 46. The remainder is 46, and that is a 46 you're seeing. That is my signature. That is my signature. So what is the signed document? Signed document, the message we had and the signature. The message was 6, the signature is 46. So this is the signed document. How do we verify this? We said to verify, we take the S and raise it to E. To verify, we said take S and raise it to E. E is public. What was it? It was also 7. For this question, coincidentally, E and its inverse were 7. So E is also said, let's just confirm from the question, E is 7. So we take S, raise it to 7. 46 raised to 7, mod 65. These are relatively large. So I'll not do it with the calculator once, but I'll use fast powering algorithm, which we have learned. We have learned this, but let's just again do it. 46 raised to 1 is 46. Then 46 square, what is it? Let's just use a calculator. And remember, we are doing it mod 65, mod 65. We are doing it mod 65. So let me do it. 46 square, 46 square, I'm getting 2,116. I do mod 65, which again, it means divide by 65 and write the remainder. So when I do that, 65 goes out 32 times. What is the remainder? 32 times. The remainder is 36. Now to get the next step, I square the one above. I square the one just above. So when I square this, I have 46 raised to 4. And when I square this 36, what do I get? When I square 36, I get 1,296. Remember, it's mod 65. So let me divide by 65 and then write the remainder. 65 goes there 19 times. What is the remainder? The remainder is 61. Now, if I try to square it, I'll get 46 raised to 8. But that is not what it's beyond what I want. What I want is 46 raised to 7. But trying to square this again will give me 46 raised to 8. So it means this is the end of squaring. So then I use what I have to get what I want. I want 46 raised to 7. So I use what I have here. What I have raised to 4, raised to, and so on. So I can see to get 7, power 7, to get power 7, I need 4 plus 2 plus 1. This gives me 7. 4 plus that is 6, means that's okay. So just expanding this, using the law of indices, this is 46 raised to 4 multiplied by 46 raised to 2, then multiplied by 46 raised to 1. That's what I wrote here. So then what is 46 raised to 4? You go back to what you have. We just clear this. What do we have? 46 raised to 4, we have it. It's 61. What about 46 raised to 2? We have it as 36. What about 46 raised to 1? We have it as 46. Let's multiply. And we are doing that mod 65. Whatever we are doing here, we are doing it mod 65. So what is it? Just use a calculator again. Use yours. Use your calculator so that we get the same result. 61 times 36 times 46. I'm getting 101. Just a minute. I'm getting 101,000. And then 0.16. And I'm doing this mod 65. In other words, I'm dividing by 65 and noting the remainder. So when you divide this by 65, it goes there 1,554 times. 1,554 times. Let's see. 1,554 times gives me a remainder of 6. If it goes there those number of times, the remainder is 6. So you can see, I'd said that you take your S raised to E, see what you get, and then compare what you get with what you are sent as the signed document. You can see the signed document has a 6. So we're just comparing what we've gotten here with what is inside here. We want to see whether what is inside there is true. And so we verified actually that this document was signed by the person who sent us. Now, so there was part B, and again, we want to try this, part B. Part B, he chooses P to be 7, then Q to be that, then E. And remember that this E is what we'll be using to verify. And then the message is 7. The message is 7. So you know what we're supposed to do therefore. We're supposed to find the product of the two prime numbers P and Q, and then you'll have phi of the product of P and Q, that product. You'll have phi of that product. And then after that, we shall get the inverse of E mod you'll have phi of N. And that inverse, we shall call it D. And this is what we shall use to assign our document. Let's go to our working. I think I've gone beyond that. Okay, it's here. So we're given 7 and 19. And their product is 133. What about the Euler phi of N? Euler phi of N will be 7 minus 1 multiplied by 19 minus 1. And that's how I get 6 times 18. Because 19 minus 1 is 18. And that gives me 108. Now I want to get the inverse of 5. Because E was 5. E was 5. So, and I know that 5E and D are congruent to 1 modular phi of N. In other words, D is the inverse of E. In other words, D is the inverse of 5. Phi of N we found to be 108. So that is this equation. So from there, we now use the Euclid's algorithm, just as we've done before. The previous question, we're asking ourselves, how many times does 5 go into 108? And the answer is it goes there 21 times. And the remainder is 3. This one, just using a calculator. Just using a calculator, just taking 108 and then dividing by 5. Let me just again do it. 108 divided by 5, 21 times. And then what is the remainder? What is the remainder? The remainder is 3. So you are just doing that. Then asking yourself, how many times does 3 go into 5? And 3 goes into 5 once. And the remainder is 2. And then you ask yourself, what about this remainder into 3? How many times? So 2 goes into 3 once. And the remainder is 1. Once you reach here, the next step will give us a remainder of 0. So it means the step just above the remainder of 0 is giving us this remainder as the GCD. This remainder becomes the GCD. That's how we said it earlier. So when we were doing Euclid's algorithm and extended Euclid's algorithm. So our GCD is 1. It's this one that we make the subject. We solve for it. We solve for it. So let's just see what we have here. Let's see what we have here. These inverses, these remainders. What do we have here? Then it's telling us that 1 is the same as 3 minus 2 multiplied by 1. 2 multiplied by 1. I'm just making the remainders the subject of the formula. I'm just solving for the remainders here. And the second equation is telling us that the remainder is 5 minus 3 multiplied by 1. And then the first equation here is telling us that the remainder is 3, which is 108 minus 5 multiplied by 21. So these are the remainders when I write them on the left side of the equal sign. Now I want to make this one the subject. So we just write it here. This is the first equation. We write it there. Where we have this remainder, 2, we substitute by the equivalent. So this 3 is that, and then minus 2, but 2, the equivalent is here. 5 minus 3 multiplied by 1. Then this 1 is the one you're seeing here. At this point, you just open the brackets using the minus and the 1 that are outside the brackets. Write it here, 3. Then this minus times 5 will be minus 5 times this 1. This minus times this minus gives us positive 3 times this 1. So let's collect what have the 3's together. So this is what we have, 3 plus 3 multiplied by 1. So when you 3 goes here once, and 3 goes here also once. So this is 3 times 2. That's what you see here. You're also seeing something. You're also seeing that I had negative 5 multiplied by 1, which is just the same as 5 multiplied by negative 1. That's what I've written here. Now, we've replaced the first remainder and then the second remainder. So we need to replace the last remainder, 3, the last remainder, 3. You're just doing it from the bottom going up. So when you replace that, where there's 3, we just write this, and the 3 that we are referring to is this one. Where there is this 3, we just write this, so that you are seeing it in the next step. Seeing it in the next step, this part was the 3. This part is the 3. This 2 is just this. That is just that one. What we've only substituted is this 3. At this point, again, we open the brackets using what is outside the bracket. Just clear this part so that we see. This part is not affected by this bracket, so we just write it. 5 multiplied by negative 1. The bracket I'm referring to is this. There's a plus sign outside and there's this 2 outside. So when you take them inside, you would get 108 multiplied by 2. This plus times this minus will be minus 5 multiplied by 42. Again, we can see 5 appearing twice. So how do we go about it? We just take this 5 minus 1 minus 5, 42, and factor 5 outside. When you factor 5 outside, it goes here minus 1 times, and it goes here minus 42 times. And so this is the same as 5 multiplied by negative 43. That's what you're seeing here. This other one just remains the way it is. 108 times 2. 108 times 2. What we were looking for was D. And what is D? D is that number which, when multiplied by E, gives us 1. That number which, when multiplied by E, gives us 1. But in this case, our E is 5. So the number that is multiplied by 5 to give us 1 is negative 43. So D is negative 43 mod 108. which we just make positive. And the easier way I told you was just to add these two numbers. Add this to this until you get a positive number. Add it until you get a positive number. And for this case, it's just once. You just add it once and get this. The alternative way that I showed you was just take 108, because this one means the remainder when 108 goes into negative 43. How many times does 108 go into negative 43? It goes there negative 1 times. So negative 1 times this, you get negative 108. Then subtract this. So I'm taking negative 43 minus 108, which gives me 65. And of course, I had told you earlier that if you don't know how to get this negative 1, the easier way I told you, assume that the negative 1 is not here. 43, assume that 43 does not have negative 1. Then divide by 108. You will find that 108 will go there 0 point something. 0 point something. So now if it had a negative, just a minute. So let me just again explain. So I've taken the 43 and assuming it has no negative. I'm dividing by 108 and I'm getting that it's going there 0 point something. So then I approximate this number, I take it to the next whole number. The next whole number. So the next whole number is 1. Then you just give it a negative sign. So then that means 108 goes to negative 43 into negative 43, negative 1 times. So let me just explain again. I just divided 108 into 43. And this time I was assuming that 43 did not have a negative sign. And I discovered it was going there 0 point number of times. So then I make that the next whole number. Because what I have is 0. So the next whole number is 1. The next whole number is 1. So that 1, I just give it a negative. Then I come and do my long division here. Now, so we just found that D is 65. Just use the extended Euclid's algorithm and found, of course, it was, first of all, it was negative 43. And we've made the negative 43 positive. And so negative 43 is congruent to 65, mod 108. Now, so I want to sign our document. What was the document? Our document was 7. Our document was 7. So this is what we want to sign. We know how to sign it. We know that for us to sign it, we raise it to D. We raise it to D. This is 7 raised to 65. And then we use the extended Euclid's algorithm. 7 raised to 1, okay, 7 raised to 1 is 7. This one, 7 raised to 2 is that. And then square this to get the next. So the next is 7 raised to 4. So I arrange them that way just because of space. So let me just take 49 square. 49 square. 49 square is 2,401. Remember our mod, 133. So when I divide this by 133, it goes 18 times. 18 times and the remainder is 7. What about squaring this? I'm supposed to get this one, the next one. When I square this, I have 7 raised to 8 and 49. Now squaring this gives me the next one. And it is just the same as when I did that, I got 7. So again, squaring this should give me 49 and so on. This first pairing algorithm, we've done it quite a number of times. I know we are very much familiar with it. Now, so we did up to 7 raised to 64. And we knew that doing squaring this one again will have given us 7 raised to 128, which is above what we want. What we want is just 7 raised to 65. So 7 raised to, what is 65, of course? 65 is just 64 plus 1. So that means 7 raised to 65 is the same as 7 raised to 64 times 7 raised to 1. But 7 raised to 64 is 7. And 7 raised to 1 is also 7, which gives us 49. That is our signature. 49. That's our signature. What is our signed document? The message we had, which was 7, combined with the signature. We want to verify whether the document we've been sent is true. This is what we've been sent. Want to see whether it's true? We take S and raise it to E. Our E was 5. Mod 135. These are very small numbers. This one you can just do with your calculator at once and then divide by 133, and the remainder is that. Let's look at the next example. At the next example, you're told that this Linet uses RSA signature with the public modulus 55. And then there is the encryption exponent, which you've been calling E, is 7. She then sends these 3 documents, or she then sends 3 documents to Alex with her signature attached. Alex creates a 4th document to unsuccessfully try and forge. These are possibly Lynette's signature. So he tries to forge Lynette's signature. So the question is, which of these 4 is forgery? Which of these 4? So we have 1, 2, 3, 4 documents. Lynette had sent 3. And then Alex has tried to forge 1. So the question is, which of these 4 is forgery? So as we said, once you do with RSA properly, anybody trying to forge your new may not manage if you have done it properly. Using large prime numbers and so on, trying to forge it will be impossible. And again, if you did it properly, again, you cannot deny that it's not you who did it, because it's only you who has a D. D is a private signature. Is a private key. It's only you who has it. So you cannot deny that it's you who signed it. I want to find out which of these is forgery. Now, we don't need to calculate D. We don't need to calculate D because we've been given the signed document. These are signed documents. These are signed documents. So we've been told that she sends 3 documents. First of all, yes, she sends 3 documents to Alex with her signature attached. So we then know that this is the signature. Yes, this is the signature for this one. For this one, this is signature. For this one, this is the signature. And then this is the message. Remember, what you are sending is message with S. Message with S. So our message for this document is 3. And our S is 27. So how do you normally verify? For us to verify, let's verify the first document, whether it's true. For us to verify the first document, we just need to take the S, and raise it to E, the public key. Raise it to E. What is our E? Our E is 7, more, and then the mod is 55. The mod is 55. Those two are public. They're in the public domain. So it's E mod 55. E mod 55. E7, that's okay. Let's see whether these are smaller numbers which you can just do with your calculator in one step. If they're not, we shall use the fast powering algorithm. So I'm taking 27, and then to it I'm raising 7. Oh, these are very huge number. These are very, very huge number. So if that is okay, then let's use the fast powering algorithm. Fast powering algorithm. Okay, what is 27 raised to 1? And we are doing this mod 55. This will be 27. What about 27 raised to 2? And again, is the same mod 55. Let's just do it very fast. 27 times 27 is 529. No. 729. 27 times 27 is 729. Just use your calculator so that we don't write what is not correct. Okay, let's divide by 55. Goes there 13 times. 13 times. What's the remainder? When there 13 times, just a minute, 13 times, when there 13 times, the remainder is 14. Okay, want to go up to 7 times. So 27 raised to 4 is squaring the one above, mod 55, will be 14 square. The 14 square, which is 196. 196, let's divide this by 55. Goes there 3 times. Goes there 3 times. And the remainder is 31. When we square this, it will go beyond what we want. So therefore, what is 27 raised to 7? This will be the same as 27 raised to 4 plus 2 plus 1. And we are doing this mod 55. What is this? The same as 27 raised to 4, 27 raised to 2, 27 raised to 1. And we are doing that again, mod 55. What is 27 raised to 4? Start 1. And this other one, 14. And then 27 mod 55. Let's just multiply that. Let's just multiply that. What is this? 31 times 14 times 27. I'm getting 11,718. Let's divide by 55 and then write the remainder. 55 goes there 213 times. 213 times. 213 times. The remainder is 3. We were verifying, and let's see whether this 3 is the same as the one we were sent. We were sent what? We were sent 3. This means this document is genuine. This one is genuine. It's valid. This one is valid. Let's try the next one. It's 12. No, it's 23. 23 is the signature. And what is our E? Our E is still 7. Let's see. 23 is the signature. Our S is 23. So we want to find S raised to 7, which means 23 raised to 7 mod 55. I want to attempt again and see whether it's a smaller number so that we save on time. Raised to 7. I think I can do this. We can do this. It's a small number, although it has given us with that. But let's just don't say equals. What we've done, we've found something like this. We just found something like 4 times that, then E raised to 9. There's no problem. Let's divide by 55. When you divide by 55, I'm just using my calculator, and I can see 55 has gone by 91 or 61, 95, 917.2. Has gone there those number of times. Let me just say minus. Using my calculator, let me just say minus. Let me multiply by 61, 90, 59, 17. I'm getting 12 as the remainder. Getting 12 as the remainder. Of course, you will have used fast pairing algorithm, but this one you can do it without, because these are small numbers. Let's see whether it was 12 that was sent. True, it's 12. Let's try this. I just want to try that. You'll try the next one. Of course, we've been told that 3 of these are genuine. 1 is not genuine. So what I have is, we've already tested 2 which are valid. So we just want to get to which one of these is not valid. So if this one becomes valid, then it means this will not be valid. But if this one is not valid, then this one will be valid. But of course, you can check later to see whether. So S is 12. S is 12. This time, S is 12. So S raised to 7 is 12 raised to 7 mod 55. What do you get? This, in fact, is smaller. It's a smaller number. Let's see. 12 raised to 7. Oh, I'm getting that 5 million is a small number. Just use your calculator. Use your calculator. 12 raised to 7, then divided by 55 and not the remainder. 55 goes there. 6 million, well, it's not 6 million, it's 651,487.418. What is the remainder? What is the remainder? 651,487. The remainder is 23. Let me see whether my M is 23. Whether my M is 23. What M were we sent? The M we were sent is 9. And the M we're supposed to get is 23. So you can see this is a forgery. This one was forged. It's not coming from the net. What about this? Let's just verify this. Let's just verify that. That 9. That 9. That 9 raised to 7. What do you get? Again, these are smaller numbers. That 9 raised to 7 what I'm getting is that this is not a big number. Let's divide it by 55. This one is big because the number of times going here. This one is big. So let's use first pairing algorithm. 39 raised to 1 is 39. 39 raised to 2 is 39 times 39. And you are dividing by 55. Goes there 27 times. Goes there 27 times. The remainder is 36. What about 39 raised to 4 is 36 square. 36 square. So 36 square. 36 square is 1,296. We are doing it mod 55. Goes there 23 times. Goes there 23 times. The remainder is 31. So therefore, 39 raised to 7 is just 39 raised to 4, 39 raised to 2, 39 raised to 1, which is 31 times 36 times 39 times 39. And we are doing it mod 55. So what do you get? 39. That product is 43,524. Let me divide by 55, which goes there 791 times. 791 times. 791 times. What? 791 times. The remainder is 19 mod 55. Let's see whether 19 is the M we were sent. The M we were sent was 19. Yes, this is a genuine document. It's valid. So this is the forgery. So you can see we didn't need to calculate D because D was not useful for this question. This question we are doing just verification. We're just verifying that the signature, the document that we have is valid. And so we go to the public domain. We obtain the public key from the sender. The public key the sender has. The sender has sent the public key, which is 55.7. This is the public key. So we are interested with this too, because for us to verify, we take S raised to E mod 55. So that's how we do this type of questions. Okay, I think let's stop there. Thank you.